Hi Anirudhan.
Hi, Bobby.
See, I was trying to solve some problems
Okay.
after we discussed about the MOSFET.
Okay.
I think something that we discussed towards the end of it is an inverter,
Correct.
a proper inverter.
Proper inverter. Correct. Maybe I'll draw it.
Yeah.
Is this the circuit?
Yeah.
Yeah.
But then I found something where they are connecting a resistor between the gate and drain.
Okay. So between the input and output
Yeah.
almost. Okay. Okay. Some
A
resistor R like this.
Resistor.
Oh, okay. Okay. So you want to solve that problem?
Yeah, because I was thinking there may be something new in this.
That is true. So maybe first we will see why they would even want to connect a resistor, no?
Yeah.
So one thing is, well, let us take the circuit without the resistor first. Then we can add the circuit with the resistor. So I'll move it to the side for now.
Yeah.
So I think what we saw was we applied an input. This was Vi, this was Vo.
Correct.
And we got a curve something like this. So that Vi versus Vo curve is what we derived.
Yeah.
Right. So
Exactly.
okay. Something like this.
Yeah.
So it starts all the way from VDD when the input is 0
to 0.
to 0. Now that is this circuit. So now if I just take an inverter and let's say I remove the input and output,
Okay.
and I just connect a resistor across it, I should be able to find out what the voltages and currents are,
True.
right? Well, actually theoretically, I mean that we put in the values, we'll be able to find out. But suppose I take the same inverter, we know the V out versus Vi.
Yeah.
I'm going to take that same inverter and connect the resistor, correct? So we want to find out what will happen, right? What will the input and output be?
So when the input and output are same, there will be no current through R.
There will be no current through R.
That's
correct.
all I can make sense.
That's correct. Perfect. So in fact, this gate and this gate we studied was an open circuit.
Correct.
The gate current is 0 in both sides.
Yeah.
Which means you apply KCL at this node, there is no current through the resistor.
Yeah.
So this current is 0.
Yeah.
Which means, as you said, there is some current, some I bias flowing through both transistors.
Correct.
And if there is no current flowing through the resistor, Vi has to be equal to Vo, no? This was Vi and this was Vo.
That is true.
The two voltages also have to be equal.
Correct.
So we need to find out the point on this curve where V out equal to Vi. That will tell us where we are operating for this device. Right? Does that make sense?
So that means the characteristic will not change.
Characteristic will not change. We just take the same inverter and do, we can find out, we can analyze what it is. Well, after we do that, now there is a bias current. We can use it as an amplifier actually.
Okay.
Once you do this, next step, I can take this and so let me remove all of these things. I can take this. Now that it is biased, we know how to analyze it to find the bias. I can now add, we know how to add, no?
Input and output.
Input and output. So I can add some small signal Vi, small signal Vo. This can act as an amplifier. So we have set up the operating point using the resistor.
So then we get an amplifier which is operating in that
operating around the linearly around
where
the,
it is very
where
sharp
it is very
change.
sharp. Correct.
So that means GM will be very large.
GM will be very large. You can get a very high gain amplifier. Correct. So in fact, one easy way to find out this operating point, right? We want to find out capital Vi, capital Vo. They are both equal, no? So one easy way is, once you know this characteristic, I just draw a straight line with 45 degrees. Let me start from the origin. I draw a 45 degree line.
Okay.
Right? That is actually the line Vo equal to Vi.
Because it is symmetric.
Because it's symmetric. Right? So there is no current through the resistor R, no? So we want to find out the operating point where there is no current through the resistor,
Okay.
which means VO equal to VI.
Yeah.
So the actual operating point of the amplifier of this inverter with the resistor will be this.
Almost ideally VDD by 2.
Ideally VDD by 2, right? So in fact, yesterday I think we called it VTH.
Correct.
If it's completely symmetric, this will be VDD by 2. Correct. And that's what we wanted, no? We wanted it completely
Yes.
symmetric. So that is also the point where it's almost falling very steeply.
Correct.
Right? And if you do that, you will get a lot of gain.
I think that time both transistors were in saturation.
That is absolutely right. It's a very good observation. You're absolutely right. So in this region, M1 and M2 were in
Okay. Yeah.
saturation. In fact, we already told them, no, when you want to build a good amplifier,
True. Yes.
you want to put all transistors in saturation.
Correct. Correct.
Right?
Correct.
Because in the linear region, it acts like a resistor.
Yeah.
You won't get amplification.
Yeah. Oh. So we will see what the question was.
Sure. Let's do that. I hope the question is using a symmetric inverter.
Yeah. So it says the KNW by L and KPW by L both are same.
Okay.
1 milliampere per watt square.
Okay. So this is an example, no?
Yeah. They are matched.
Okay, perfect. So sorry, 1 minute. I will paste this circuit
Yeah.
and Vi and Vo, right? So
Yes.
you are given K prime W over L.
Yes.
It explicitly says it as K prime W over L.
Yes.
We'll just call that K,
Sure.
correct?
Yeah.
That K prime is, so we'll also tell the students now. So normal, lot of textbooks, K prime is used to represent mu Cox.
Okay.
So if you say Kn prime, it is mu n Cox, and they use Kp prime to say mu p Cox, and then you multiply this with the dimensions of the transistor. And I think what we did was we said Kn mu Cox
W by L.
W by L. This in their representation is K prime times W over L. We just replaced this with some K. So we basically said our representation is half K into VGS minus VT the whole square.
Yeah.
Right? This is the representation we have used. K prime times W over L is K.
Correct.
Lot of textbooks might give it as K prime. Students should understand. This is just for their reference.
Actually, this mu and Cox is just that wafer property.
The wafer property, correct. It's a property of the semiconductor, right? Normally, it is given to you.
Correct.
If you want to analyze or design any circuit, you need to know that.
And while design, as we discussed earlier, what we can change is W by L.
W by L. So, which is why they have, like you said,
Split
it, correct. And to make things easy for our students, we have even included WL also inside and called it K. That's all.
Correct.
It makes it easy. So, they have given K, no?
Yeah. It's
So
1 milliampere per volt square.
1 milliampere per volt square. Nice. So the units of K. So we didn't mention it in class yesterday, but I mean in the previous lecture. But it should be clear that it should be in ampere per volt square. Basically, current over volt square.
Correct.
Perfect.
Kn is equal to Kp.
Oh, perfect. Easy.
And Vt is 0.5 volt.
For both devices.
Both devices.
Oh, perfect. Easy. So it's completely symmetric.
And the resistor R is 1 mega ohm.
Okay. Okay, R is 1 mega ohm. And is VDD given?
So VDD is 1.5 volt.
1.5 volts.
And bottom is not grounded. That's minus 1.5.
Okay. Great. Perfect.
And gate and drain. Okay, so the question is for G and D open. That means there is no current through
There is
R.
no current through R, correct.
What are the drain currents? ID1 and ID2.
Perfect. So now we know that ID1 and ID2 are equal, first of all.
Yes.
Right? So we are just calling it IB.
Yes.
Right? So our job, what is the value of IB? right? That is the question for us.
Yeah.
Okay.
Oh, anyway, now we know both are in saturation.
We know both are in saturation. So that we just discussed just now.
Correct.
That symmetrically. So just one thing, because your supplies are minus VDD and VDD, right? So the curve will shift.
Shift to?
Because we are not
X.
going to sweep from 0 to VDD, we have to sweep the input from minus VDD to VDD.
Yeah.
Right? And so when the input is plus VDD, right? The output will no longer be 0. The transistor will turn off when the input goes closer to minus VDD.
So 0 is replaced with minus VDD.
That is all in the curve. Correct.
Yeah.
You can just use the same curve, except this should be minus VDD.
Yeah.
You can imagine it like that. Correct? Yeah. Perfect. And this will also be minus VDD. X, it goes from minus VDD to VDD. That is all. You can just imagine that the axis is shifting.
So this transition ideally will happen at 0.
At 0, correct,
Okay.
perfect, correct.
Okay.
So maybe I'll copy, instead of changing this,
Yeah.
I'll copy the same curve
That will be better.
to the next page.
Yeah.
Maybe I'll put it here. So we'll call this M1 and M2.
Yeah.
So what we are saying is that earlier the threshold voltage was VDD by 2, but now we are, because ground is changed to minus VDD, so you will sweep the input from minus VDD to plus VDD. And the output will go from VDD plus VDD to minus VDD. So I'll show that as well here. And now this VTH ideally for a symmetric will be, originally when it went from 0 to VDD, it was at VDD by 2.
Yeah.
Now it should be at 0.
Yeah. But is this very common?
It is rare.
Right.
It is
Yeah.
very rare
Yeah.
that you
Just
see
for a
CMOS.
problem, it's,
Just for a problem, it is
yeah,
useful.
yeah.
But it's very rare that you see a CMOS chip or
Going to negative.
going to negative voltages. Right? Normally it
Mostly
is
unnecessary, I think.
mostly unnecessary. Correct. But for this problem purposes, it's fine.
Yes. Yes.
So maybe we'll make the problem very easy for us. Since we know that it is symmetric.
Yeah.
Same threshold voltage, same Kn. The first assumption we will make is this assumption is valid.
Yeah.
VTH is 0.
Yeah.
Right? So which means the transistors are biased such that input equal to output. So using that symmetry, no, we will say Vi equal to Vo is the threshold of the inverter, which is 0 volts.
Yeah.
So that I think is a good assumption, right? Now we just have to solve the transistor equation to get the bias currents, right? I think this is relatively easy.
Yeah.
We can solve it for either M1 or M2, right? It's completely symmetric. We will just solve it for M1.
Yeah.
So ID is half Kn VGS1 minus VTN the whole square,
Yeah.
which is the bias current that we are trying to solve. 1 milliamp per volt square, ampere per volt square, into VGS1 is Vi minus VDD.
Yeah.
So 0 minus 1.5 minus Vt
0.5.
is 0.5. Whole square. Half Kn, VGS1 is 1.5 minus 0.5.
Yeah.
Oh, this is easy calculation also. 1.5 minus 0.5 is 1.
One.
1 squared is 1. So it is just,
Kn is also 1.
Kn is also 1. So it is basically half an ampere, half a milliampere.
Milliampere.
Half a milliampere. Oh, easy. This became a very easy problem because we used the symmetry.
So IB,
Ah,
not the base or
Not the
bias
base current.
Okay.
Correct. So shall we use a different one?
Yeah.
So just so that we want, I'll call it like this,
Yeah.
high bias. We'll change it everywhere.
Yeah.
I know, you're absolutely right. We have to be very careful.
Yeah.
Okay.
Nice problem.
Nice problem. Yes. And actually, a lot of cases for a high gain amplifier, I see in IC design people using this quite commonly, this kind of amplifier. We'll do one more problem.
We'll do one more.
Sure.
Just to get some more grip.
Sure. I like this problem because there was both NMOS and PMOS.
Yeah.
So maybe one more problem also we'll do like that.
Sure, sure.
Why don't you suggest?
This time we will split that connection between the gates.
Ah, okay. So you don't want the inverter style gate and
Yeah.
the two gates connected together.
Yeah.
Okay. So let me draw it. You tell me. So you are saying that you take the same inverter but disconnect one of the gates, no?
Yeah.
Which gate do you want to
We will
disconnect?
give input to M1.
Input to M1. Okay.
The other one we will just connect it to.
You want to connect it to what?
So this is source drain, no?
Source drain. Correct.
So
Source,
we connect it to
gate,
drain.
Ah, you want to connect it to the drain. Okay, perfect. Like this?
Yeah.
Oh, nice. This is actually like the current mirror connection.
You have used this to sense that voltage.
Sense that voltage. Correct. We have done that, no, for the current mirror. Nice. Okay.
So you were saying that this will be in some
In saturation.
saturation.
Correct. So I think the condition was that for the PMOS transistor in this case. So we said that the condition for the PMOS transistor. So this was source voltage, gate voltage, drain voltage. So if the drain voltage was less than or equal to Vg plus Vtp, so the drain voltage is smaller than the gate voltage
Yeah.
plus Vtp, then the PMOS transistor is in saturation. Okay. In this case, Vtp is, let's say 0.5, say we'll take the same value as before. So definitely Vg is equal to Vd is equal to Vg in this case.
Yeah.
Definitely it is in saturation because it can go for another half a volt higher before it hits the border of the linear region. So M2 is in saturation.
So for a wide range, this will be in
Correct.
saturation.
Correct. That's right.
Okay. So we will apply the same parameters of the previous problem.
We will do that. That is easy, no?
Yeah.
So I think we said Kn and Kp are 1 milliampere
Correct.
per volt square.
Correct.
So we'll assume the same thing.
Yeah.
And Vtn and Vtp were both 0.5 volts.
Correct.
We'll take minus VDD and plus VDD or 0 and
0 and VDD.
0 and VDD. So maybe we'll make it 0 and 3 volts.
Yeah.
We'll just keep
Yes.
the
Yes.
VDD minus ground the same.
The
right?
swing is the same.
Swing is the same. Okay. Okay. So we'll do it like this. So, so now what is the question? What did you want to do?
We'll find out the ID and
We'll
then
find out
maybe
ID.
I wanted to know that output voltage also at that time.
So shall we do like this? What we will do, shall we set Vi to be VDD by 2?
Yeah.
We'll need to choose something, no?
Yeah.
So we'll choose
If Vi is.
correct. So if Vi equal to VDD by 2,
What is ID?
what is ID? So clearly here also there is no gate current
Yeah.
through M2. So ID1 is equal to ID2.
Yeah.
Right? So that also we know. So we want to find out ID1, let us say. Okay, let's do it. This is easy, I think.
Yeah.
Well, I think let us say we want to find out ID1 and we also want to find out the drain voltage of M1. So maybe VD1.
Correct. Correct.
These two we want to find.
Yeah.
So that will give us one more thing to do. Finding ID1 is relatively straightforward.
Yeah. It may be the same value.
It may be the same value, right? Because VGS has not changed.
Correct.
Right? It is still, earlier it was 0 minus VDD,
Yeah.
1.5 volts.
Correct.
Here also it is the same thing.
Correct.
Right? So we'll just write it, but we
Yeah.
expect the same value.
Yeah.
ID1 is half into 1 milliampere per volt squared into gate voltage is VDD by 2, 1.5 minus source voltage is 0 minus VT is 0.5. As you clearly pointed out, it's the same as before, right? Perfect. So the bias current of both M1 and M2 is 0.5 milliamperes,
Yes.
same as before. Perfect. But now we want to find out VD1. How do we find that out? We can't find that out using the equation of M1 because M1 in saturation, there is no dependence of current on the drain voltage.
Correct. Correct.
Right? So we don't know. We have to use M2.
That's also in saturation.
That is also in saturation. But
It is
we can find
connected.
out the gate voltage
Correct.
and the gate and drain are shorted. That is the only way to find out. Right? Okay. So shall we find out the
Gate voltage.
gate voltage of M2?
Yeah.
Okay. So VD
Same current is going.
same current is flowing through M2.
Yeah.
So we'll say ID2. We'll use the ID2 equation.
Yeah.
So for same current is flowing through 0.5 milliamperes is half into Kp, right?
Correct.
Which is also 1 milliampere per volt squared into, we don't know the gate voltage.
Yeah.
So we need to do VSG minus VT.
Yes.
Vs is 3 volts minus we don't know what the gate voltage is, which is VG2,
Yeah.
which is the same as VD1,
Yeah.
which is what we want to find. I'll write it directly here. Minus 0.5, which is the VTP,
Yeah.
the whole square.
Also
This
VD. Yeah.
Correct.
Yeah.
So from this we can find out VD1.
Correct.
So we have 0.5 milliampere. This is also 0.5 milliampere.
Yeah.
So it looks like 3 minus VD1 minus 0.5 squared is 1.
Yeah.
Right? So 3 minus 0.5, 2.5. This is the equation we are getting.
Yeah.
3 volts minus 0.5 volts is 2.5 volts minus VD1 whole squared. These two are equal, so it is just 1. Right? So which means VD1 is 2.5 minus 1, 1.5.
Yeah.
Actually, it is the same value as before, no? It is the same value as we got in example 1,
Yes.
right?
1.5.
1.5. Actually, I see why. So, in the previous problem, no, there was no current through R. So, we had biased it such that V out was equal to VI.
Correct.
We chose VI,
same point.
the same point. Everything worked out such that it was the same value.
Then actually what is different in the circuit?
The difference in the circuit, the fact that we have changed the, actually the input output bias point is the same,
Bias point is same.
but the input output characteristic will be completely different for this.
Because the previous circuit, both transistors are in saturation only for
A very
small
short,
VI.
small range of voltages, input voltages.
While here
Correct.
this will be
Over a large
valid for
range.
a
Actually, what you're saying is correct. See, whenever there is current flowing through M2, M2 is in saturation,
yeah,
right?
yeah,
Only point when M2 goes to a different region, so M2 never goes to triode,
yeah.
right? So I am imagining,
M1 will go at some point.
correct. So if I look at this curve, no, we are not going to draw the full curve, but if I plot VO versus VI for this inverter, well, we don't know if it's an inverter, but we hope that it's an inverter. So if we plot VO versus VI for this circuit, I can already see that if VI was very large, so if VI was 0, no, M1 is off, output voltage will be at VDD.
VDD.
That one we can tell,
Yeah,
right?
So
but if
till VT,
till VT it will be flat.
yeah.
But after that, no, we had a point where M2 was in triode originally. That will not happen. It is in saturation.
Yeah.
In fact, I also noticed one more thing.
Hmm.
If I make Vi equal to VDD, very large current is flowing. Actually, it will never go to zero. The output voltage. It will do something like this. I think it will never go to
Yeah.
zero. That's what it seems like. Because there will be some current flowing, no?
Correct.
Through
Correct.
M2 and M1.
Yeah.
It looks like it will never go to zero. So,
But the input voltage that you can give
can go from 0
for
to VDD.
amplification
For
is,
amplification is correct.
but the gain will be low.
Gain
compared
will
to-
be lower. Correct.
Nice.
So in fact, I have shown it exaggerated, but it'll probably be more like this. It'll be a very not so steep curve,
Yeah.
right? It'll be a not so steep curve
Correct,
completely. Correct. So the gain is much lower. Correct. So I think in a future course, if the students take, they will learn more about transistors, devices, characteristics, and so on. They will learn more in such a course.